The images shown in this video do not follow the exact sequence of the narration. Some of the technologies were fully built, while others existed only as prototypes or conceptual designs. The final years of the Second World War witnessed a dramatic shift in German military strategy, facing overwhelming Allied production, collapsing supply lines, and continuous battlefield losses. Nazi leadership turned increasingly toward technological miracles or wonder weapons that they believed could restore initiative and alter the course of the conflict. These weapons included long-range missiles, jet aircraft, guided munitions, and experimental armored vehicles of unprecedented size. Although many of these projects demonstrated exceptional engineering skill, they emerged too late, in insufficient numbers, and under conditions that made strategic success impossible. The origins of Germany's Superweapons program stretched back to the interwar years. Restrictions imposed by the Treaty of Versailles limited conventional armaments, but did not anticipate new fields such as rocketry and jet propulsion. German scientists and engineers exploited this gap. Early rocket experiments began in civilian clubs and research institutes, eventually attracting military interest. By the mid-1930s, the Army Weapons Office established formal research programs at Kummersdorf and later at Pien, where Werner von Braun and his team began designing rockets capable of long-range flight. The first major result of this work was the Fieseler V1, later designated the V1. Unlike earlier experimental rockets, the V1 was a pulse-jet-powered cruise missile designed for mass production. Its simple construction, sheet metal wings, a pulse-jet engine, and a basic guidance system allowed rapid manufacturing. The V1 carried a warhead of approximately 800 kilograms and could be launched from fixed ramps or aircraft. Although crude by modern standards, it represented one of the earliest operational standoff weapons. The German leadership viewed it as a strategic tool capable of striking British cities without risking aircrews. Development of the V2 followed a different trajectory. The V2 was the world's first ballistic missile, a liquid-fueled rocket capable of supersonic flight and suborbital trajectory. It represented a monumental engineering achievement, weighing nearly 14 tons and standing over 14 meters tall. The V2 used a complex engine burning liquid oxygen and alcohol. Its guidance system combined gyroscopes and aerodynamic fins to control flight. Upon launch, the rocket reached speeds exceeding the sound barrier, making it impossible for Allied defenses to intercept. When it struck, the V2 delivered a 1-ton warhead with devastating kinetic force. Research at Peenemünde expanded rapidly under military pressure. As Allied bombing intensified and the Eastern Front deteriorated, Hitler demanded weapons capable of delivering decisive blows. The V1 and V2 programs received top priority. Thousands of engineers, technicians, and forced laborers were mobilized. Underground production facilities were constructed to protect manufacturing from air raids, particularly the massive middlework tunnels near North, where prisoners from Mittelbadora performed labor under brutal conditions. The Superweapons program consumed enormous resources at a time when Germany lacked fuel, steel, and skilled manpower. Germany's pursuit of jet propulsion followed a parallel path. Early German research into turbojets predated the war, but official interest increased sharply after 1940. Engineers such as Hans von Ohain and Anselm Franz developed practical turbojet engines that could power high-speed aircraft. The Messerschmitt Me 262 became the first operational jet fighter in history. With a top speed far exceeding Allied piston engine fighters, the Me 262 represented a genuine technological breakthrough. Its firepower 430mm cannon made it lethal against bomber formations. Yet jet development faced immense obstacles. Production was delayed by disputes within the Luftwaffe, shortages of heat-resistant alloys, and Hitler's insistence that the Me 262 be configured as a fighter-bomber rather than a pure interceptor. Material shortages forced the use of inferior metals, reducing engine lifespan to a few operational hours. Fuel scarcity further limited training and deployment. Despite its advantages, the Me 262 entered combat too late and in too few numbers to alter the air war. Allied forces maintained overwhelming numerical superiority and continued destroying German infrastructure. Germany also experimented with rocket-powered aircraft such as the Messerschmitt Me 162. This interceptor used a liquid-fueled rocket engine that provided exceptional climb rate and speed, but flight duration was extremely short and the volatile fuel mixture made operations hazardous. The aircraft was difficult to fly, dangerous to maintain, and tactically limited. Its successes were isolated, and its losses high. Nevertheless, the Me 163 demonstrated the depth of German innovation, even if its battlefield utility remained low. Beyond missiles and jets, Nazi planners pursued armored vehicles of extraordinary scale. The most extreme example was the Panzerkampfwagen 8 Maus, the heaviest tank ever built. Designed by Ferdinand Porsche, the Maus weighed nearly 200 tons. Its armor was so thick that no Allied anti-tank gun of the period could reliably penetrate it. However, its massive weight made it impractical. It could not cross most bridges, consumed enormous fuel, and moved slowly. Only 2 prototypes were completed before the war ended. Similar projects, including the E-series tanks and conceptual designs for multi-hundred-ton vehicles, reflected unrealistic expectations rather than strategic logic. The German Navy also sought Superweapons. Designs included advanced U-boats with increased underwater endurance, snorkels, and improved torpedoes. Late-war submarines, such as the Type 21, featured streamlined hulls, enhanced battery capacity, and quiet electric propulsion. These boats represented a leap forward in submarine technology, influencing post-war navies across the world. However, production delays, sabotage, and the collapse of German logistics prevented their deployment in sufficient numbers. Across all these programs, a common pattern emerged: remarkable engineering, unrealistic expectations, insufficient production, and catastrophic timing. Germany's industrial base was collapsing, fuel supplies dwindling, and labor forces stretched beyond capacity. Superweapons consumed vast resources without providing strategic advantage. They represented a desperate attempt to overcome material inferiority with technological superiority, a gamble that could not succeed against the combined industrial might of the Allies. By early 1944, Germany's superweapons program had become both a symbol of desperation and a centerpiece of Nazi propaganda. Hitler increasingly believed that advanced technology could compensate for Germany's collapsing strategic position. The propaganda ministry portrayed the weapons, jet fighters, and megatanks as instruments that would reverse the Allied advance. In reality, these systems, though technically impressive, were deployed under conditions that guaranteed limited impact. Their development illustrated the widening gap between German technological ambition and Germany's declining industrial capacity. The V-1 campaign began in June 1944, shortly after the Allied landings in Normandy. Hundreds of launch sites in northern France and Belgium were prepared for continuous bombardment of London and other British cities. The V-1's simple construction allowed rapid production. Launched from inclined ramps, the missile flew at relatively low altitude, its pulse jet engine producing the distinctive buzzing sound that earned it the nickname Buzz Bomb. When the engine cut out, the missile entered a dive toward its target. Although the V-1 lacked precision, it delivered significant psychological impact. British defenses responded quickly. Radar-guided anti-aircraft guns, barrage balloons, and fighter interceptions steadily reduced the effectiveness of the V-1 campaign. Allied bombers targeted launch sites, fuel depots, and transportation networks, supporting the program. As ground forces advanced across France, the majority of V-1 launch bases were overrun. Germany attempted to shift to air-launched V-1 south, but fuel shortages and Allied air superiority limited these operations. Despite launching more than 10,000 V-1 south, Germany failed to achieve strategic disruption. Damage in London and other cities was significant, but the campaign consumed resources that Germany desperately needed on active fronts. The V-2 presented a different challenge. Unlike the V-1, the V-2 could not be intercepted. After launch, the rocket traveled faster than the speed of sound, reached altitudes above 80 kilometers, and descended onto its target with tremendous kinetic force. The first V-2 strikes on London in September 1944 stunned the Allies. There was no warning, no defense, and no countermeasure capable of stopping them. The psychological shock was immediate. However, the V-2 program suffered from severe limitations. Each rocket required complex fueling, delicate handling, and extensive support equipment. Launch teams had to operate in mobile formations, constantly relocating to avoid detection. Allied intelligence and air power responded aggressively. Bombing campaigns targeted the Peenemünde Research Center, forcing the program to disperse. Underground factories were attacked repeatedly, although many remained operational due to Germany's extensive use of forced labor in hardened facilities. Mobile launch crews faced constant pressure from Allied reconnaissance and ground advances. While more than 3,000 V-2 Souths were eventually fired, their overall military impact remained limited. The rockets lacked precision, their warheads were small relative to the strategic cost, and they diverted critical materials from conventional weapons. Production jet aircraft represented Germany's most promising technological advantage. The Me-262, with speeds approaching 900 km per hour, could easily overtake Allied fighters and strike bomber formations with devastating effect. Experienced Luftwaffe pilots regarded the aircraft as a potential war-changing asset, yet production and deployment faced persistent obstacles. Allied bombing campaigns targeted engine plants, airfields, and transportation networks, delaying output. Shortages of high-grade alloys forced engineers to use substitutes that caused rapid engine wear. Many Me-262s were lost not to combat but to mechanical failure during takeoff or landing. Hitler's interference further weakened the jet program. Convinced that Germany needed offensive weapons to strike Allied ground forces, he ordered that the Me-262 be configured as a fighter bomb. This requirement delayed deployment by months and forced structural modifications that reduced its performance in the interceptor role. By the time the jet entered combat in meaningful numbers, the Allies had already secured air superiority with overwhelming numerical strength. Me-26T units achieved tactical success, coast-destroying bombers and surprising escort fighters, but could not affect the strategic course of the war. Other jet innovations included the AR-2, the world's first operational jet bomber and reconnaissance aircraft. With high speed and long range, the AR-234 offered capabilities unmatched by Allied aircraft. However, production never reached necessary levels, and fuel shortages restricted operations. German jet reconnaissance missions provided valuable intelligence, but the aircraft's impact remained limited by Germany's worsening logistical situation. Rocket-powered aircraft such as the Me-16 showcased Germany's experimental spirit but also highlighted the regime's disregard for practicality. The rocket interceptor could climb rapidly to bomber altitude, but its endurance was measured in minutes. Pilots faced extreme risk from volatile fuels and dangerous landing characteristics. Training accidents were frequent, and combat effectiveness was inconsistent. While the aircraft demonstrated impressive performance in controlled tests, it was ill-suited for sustained air defense. On the ground, Germany pursued colossal armored vehicles. Believing that super-heavy tanks could resist Allied firepower and dominate defensive engagements, the Maus, weighing nearly 200 tons, embodied this philosophy. With armor thicker than any Allied gun could reliably penetrate, the tank represented engineering extremes. However, its weight prevented it from crossing bridges, navigating soft ground, or moving at acceptable speeds. Fuel consumption was immense, maintenance overwhelming, and transportation nearly impossible. Only 2 prototypes were completed, and neither saw meaningful combat. Other heavy tank concepts, the E-100 series, the Elway project, and even more extreme designs remained on paper or in early development. These projects diverted engineering talent and industrial resources away from practical weapons desperately needed at the front. Germany's belief that super-heavy armor could counter Allied numerical superiority proved unrealistic. Mobility, reliability, and logistics, not raw armor, determined battlefield outcomes. Submarine development offered one of Germany's most advanced late-war technologies. The Type 21 U-boat introduced revolutionary improvements, streamlined hull design, high underwater speed, large battery capacity, and quiet electric propulsion. This submarine could remain submerged far longer than earlier models and posed a significant threat to Allied shipping. However, production faced sabotage, material shortages, and rushed assembly, resulting in severe defects. Only a few Type 21s became operational before Germany surrendered, too late to influence the Battle of the Atlantic. Across all these programs, Germany faced the same fundamental problems: insufficient fuel, inadequate materials, disrupted production, and overwhelming Allied air power. Technological innovation could not compensate for the structural weaknesses of the German war economy. The pursuit of superweapons reflected desperation, not strategic clarity. While these weapons demonstrated engineering brilliance, their deployment occurred within a collapsing military system, unable to support them. By late 1940, for Germany's reliance on superweapons had reached its peak. The Nazi leadership, cornered by Allied advances from both East and West, increasingly viewed technology as the final hope for restoring strategic balance. Yet the deeper the regime invested into these programs, the more visible the structural weaknesses of the German war machine became. Shortages of fuel, skilled labor, and raw materials, combined with relentless Allied bombing, created an environment in which even the most advanced designs could not operate at their intended potential. The V1 and V2 campaigns demonstrated this contradiction clearly. Despite massive propaganda efforts, neither weapon matched Hitler's expectations. The V1, though produced in large quantities, suffered from declining accuracy as launch sites were pushed back by Allied ground forces. The V2, despite its technological sophistication, consumed vast amounts of alcohol, oxygen, precision components, and specialized labor. Each rocket required resources equivalent to a modern fighter aircraft jet delivered only a 1-ton explosive payload. In comparison, a single Allied bomber sortie could deliver far greater destructive power at far lower costs. The economics of the VU weapons campaign made them strategically unsustainable. Furthermore, Allied intelligence efforts gradually neutralized the VU weapons' effectiveness. Through intercepts, reconnaissance, and captured documents, analysts identified launch patterns and logistical vulnerabilities. Countermeasures included targeting supply routes, mobile support vehicles, and underground storage facilities. British deception operations directed rockets away from central London, using falsified damage reports to manipulate German targeting assumptions. Even when the rockets struck populated areas, they caused fear, but not strategic disruption. British industry continued expanding, civil defense measures improved, and public morale held firm. The story of the jet fighters followed a similar trajectory. Germany possessed a qualitative advantage, but could not capitalize on it. The Me-262 entered service too late, in too few numbers, and under operational conditions that limited its impact. Pilot shortages worsened as experienced Luftwaffe veterans were lost throughout the war. Many new recruits lacked the training needed to handle the jet's demanding flight characteristics. Fuel scarcity restricted flight hours, preventing adequate practice. Engine reliability remained low, with catastrophic failures common after only a handful of missions. Allied air superiority further constrained jet operations. Airfields suitable for jets featuring long, clear runways were priority bombing targets. Repair crews struggled to keep facilities operational under constant attack. The result was a technological marvel grounded by strategic realities. Even if Germany had produced hundreds of jets earlier in the war, supporting them with trained pilots, maintenance crews, fuel, and secure airfields would have required an industrial base that Germany no longer possessed. The Erido AR-234 faced similar obstacles. The aircraft offered exceptional speed and altitude performance, providing the Luftwaffe with reconnaissance capabilities that Allied fighters could not intercept. However, reconnaissance alone could not change the strategic situation. Attempts to convert the aircraft into a bomber faced challenges: limited payload, high fuel consumption, and the vulnerability of jet engines to sudden throttle adjustments. Although the AR-234 represented the future of aviation, it could not overcome the overwhelming Allied ground. An air campaign already in motion, rocket interceptors such as the Me-163 highlighted Germany's attempt to create specialized defensive tools against Allied bombing raids. The Me-163 could climb faster than any aircraft of the era, allowing it to reach bomber formations quickly. But its operational window was extremely short, often less than 10 minutes of powered flight. After firing its weapons, the pilot had to glide back to base, vulnerable to Allied fighters. Accidents during takeoff, landing, and fueling operations caused heavy losses. The aircraft's speed and climb rate were unmatched, yet it remained tactically ineffective. On the ground, Germany's super heavy armor program exhibited the same disconnect between technological ambition and practical utility. The Maus, though nearly impervious to Allied anti-tank weapons, required a logistical system the Wehrmacht could not provide. Transporting the tank required dismantling bridges, constructing special routes, or using rail transport vulnerable to air attacks. Fuel shortages alone made large-scale deployment impossible. Additionally, the tank's slow speed would have made it an easy target for Allied aircraft, which dominated the battlefield by night. The Maus was an engineering monument and a strategic dead end. Conceptual designs such as the Lankraiser P-100 and P-Rat illustrated the extreme fantasies circulating within segments of the Nazi leadership. These designs called for tanks weighing hundreds or even thousands of tons. Armed with naval guns and multiple secondary weapons, they were technologically infeasible, economically absurd, and militarily pointless. Their existence revealed the extent to which Nazi decision-making had become detached from operational reality. At a time when Germany needed reliable trucks, artillery, and fuel, resources were spent sketching impractical colossi that could never enter combat. Meanwhile, Germany's attempts to revolutionize submarine warfare through the Type 21 program demonstrated both potential and failure. The Type 21, with its advanced propulsion and hydrodynamic design, could operate submerged for extended periods, rendering traditional anti-submarine tactics obsolete. Had these submarines been deployed earlier and in substantial numbers, they might have significantly altered the Battle of the Atlantic, but rushed production, sabotage by forced laborers, and poor quality control left most boats incomplete or defective. Only a handful saw operational service, and none achieved meaningful success. The fate of these programs underscored a fundamental truth. Technology alone could not compensate for strategic mismanagement. Germany's leadership repeatedly invested in high-risk resource-intensive projects while neglecting the logistical and industrial infrastructure required for sustained warfare. The Allied coalition, by contrast, relied on mass production, reliable designs, and overwhelming logistical superiority. Even when German weapons surpassed Allied equivalents technologically, they could not be fielded at scale or maintained effectively. Fuel shortages were among the most crippling obstacles. Synthetic fuel plants faced constant bombing, while oil fields in Romania, the last major German-held source, were repeatedly attacked. Without adequate fuel, jet fighters couldn't train, tanks couldn't move, and submarines couldn't deploy. Many advanced aircraft sat idle on airfields, their engines unused. Experimental tanks remained trapped at proving grounds. Even V-2 launches required carefully rationed alcohol-based fuel, further straining Germany's limited supplies. Labor shortages compounded these problems. Millions of workers were killed, drafted, or displaced. Forced labor filled the gap, but under brutal conditions that reduced productivity and sabotaged output. Skilled machinists and engineers were in short supply, slowing progress on complex systems like the Me-262 engine or the V-2 guidance assembly. Allied bombing accelerated these shortages by destroying factories, transportation hubs, and power plants. Allied intelligence also played a decisive role. British and American analysts monitored German research, intercepted communications, and deciphered strategic intentions. Ultra-decrypts revealed key details about V-weapon deployments, submarine construction schedules, and aircraft production. Allied reconnaissance photographed Peenemünde jet airfields and submarine yards. Strategic bombing targeted critical nodes, disrupting supply chains essential for advanced weapons production. As a result, even promising technologies were strangled before they could reach maturity. Germany's Superweapons represented a paradox. Extraordinary talent and innovation trapped within a failing strategic system. They were born from a nation capable of remarkable engineering, yet unable to sustain the industrial and logistical momentum required for victory. In the end, the superweapons stood as symbols not of strength, but of the collapse of Nazi Germany's war effort, ambitious, impressive, but ultimately futile. By early 1945, the Nazi superweapons program had reached its final stage. Production facilities were collapsing, raw materials were exhausted, and transportation networks were disintegrating under relentless Allied bombing. Yet the leadership continued clinging to the belief that advanced technology could still deliver salvation. The pursuit of rockets, jets, megatanks, and submarines had long since ceased to be a coherent military strategy. It had become an act of political and psychological desperation. Each weapon represented the hope of a breakthrough that would never come. The V-1 program, though diminished, continued operating from mobile launch platforms in Germany and the Netherlands. These modified sites allowed the weapon to remain in use even after the fall of northern France. However, Allied air superiority made operations hazardous. Launch crews faced continuous surveillance, while supply routes were cut by bomber raids and ground advances. Accuracy degraded further as Germany lost control of forward launch areas. Many V-1s fell short, crashed on open ground, or malfunctioned due to declining quality and mass production. The missile remained a dangerous terror weapon, but by 1945 it served no strategic purpose. The V-2 program, despite vast investment, reached its operational limits. Launch units struggled to find safe positions as Allied forces approached from all directions. Production at Mittelwerk continued under horrific conditions, but output fell. Accuracy never reliable declined further as quality control deteriorated. Many rockets exploded shortly after launch, wasting precious fuel and materials. The enormous logistical burden made the V to one of the least efficient weapons of the war. For every rocket that reached its target, dozens of conventional bombs could be delivered by Allied aircraft at far lower cost. The V-2 symbolized engineering brilliance but strategic futility. Jet aircraft production faced a similar collapse. The Me-262, once considered Germany's most promising defensive weapon, suffered from a chronic lack of trained pilots and replacement engines. Fuel shortages became catastrophic. Airfields were cratered by Allied bombers, leaving jets unable to take off. Maintenance crews lacked spare parts, and many aircraft were abandoned on the ground. The few operational Me-262s achieved tactical successes, downing Allied bombers with ease, but their numbers were too small to influence strategic outcomes. The operational lifespan of each engine, sometimes less than 10 hours, made sustained deployment impossible. Other jet projects deteriorated even faster. The Heinkel Hitoet, an early jet fighter, never advanced beyond prototypes due to internal disputes and shifting priorities. The Junkers Ru-287 forward-swept bomber remained The Horton Ho 229 Flying Wing, one of the most advanced aircraft designs of its time, reached only pre-production stage. These projects demonstrated astonishing innovation, but Germany lacked the industrial stability to bring them into mass service. The story of the megatanks reached its predictable conclusion. The Mao's prototypes were tested, but remained immobile monuments to unrealistic ambition. They required special rail transport that no longer functioned, consumed fuel that no longer existed, and needed routes that no longer stood intact. Even if they had reached the battlefield, their slow speed and massive size would have made them vulnerable to air attack. The notion that such vehicles could restore German land power reflected a total misunderstanding of the realities of modern mechanized warfare. Other Super-50 tank concepts were abandoned before completion. Engineers and production staff were reassigned to more urgent tasks. Though by 1945, even these efforts were largely symbolic. Germany no longer possessed the infrastructure to produce tanks in meaningful numbers, let alone experimental machines requiring extensive machining and rare materials. Submarine development, once a proud pillar of German naval strategy, collapsed under the pressure of the Allied maritime campaign. Type 21 submarines, technically revolutionary, rolled out of factories faster than crews could be trained to operate them. Many boats were incomplete, suffering from faulty welds, misaligned hull plates, and defective batteries. Sabotage by forced laborers further degraded quality. A handful of Type XX's attempted operational patrols in the war's final weeks, but none achieved decisive results. The super submarine program illustrated the central paradox of German innovation. advanced designs hindered by a collapsing industrial base. By this stage, Allied forces had captured so many German research facilities that the future of these technologies no longer lay in German hands. Peenemünde fell to the Soviets, who captured engineers, documents, and hardware. American forces seized middlework and transported key personnel including von Braun and much of his rocket team to the United States under Operation Paperclip. Jet aircraft, submarine prototypes, guidance systems, and advanced materials were all examined by Allied engineers. The war's final months saw the transfer of German innovations into the hands of the victors, shaping post-war technological development. The Allied evaluation of German superweapons revealed a consistent pattern: brilliance in concept, but fatal weakness in execution. The technology itself was often far ahead of its time, yet the strategic environment in which it was deployed guaranteed failure. Germany lacked the industrial depth to mass-produce advanced engines, precision electronics, and high-grade alloys. It lacked the fuel to power fleets of jets or megatanks. It lacked the air superiority necessary to protect assembly lines, test facilities, and launch sites. Most of all, it lacked the time needed to integrate these weapons into coherent operational doctrine. Ultimately, Nazi Germany's reliance on superweapons highlighted the collapse of its strategic reasoning. Instead of addressing the core weaknesses of the war effort, logistics, manpower, production, and coalition strategy, the leadership pursued increasingly unrealistic technological solutions. Hitler's personal obsession with miracle weapons distorted priorities, diverted resources, and undermined efforts to produce proven systems at scale. Engineers and scientists produced remarkable innovations, but their achievements were suffocated by political interference and economic decay. The legacy of these programs shaped the post-war world profoundly. The V-2 rocket became the foundation for both American and Soviet ballistic missile development. German jet engines influenced jet aviation across Europe and the United States. The Type 21 submarine became the model for post-war designs. Concepts such as flying wings, swept wings, guided missiles, and advanced control systems accelerated global technological progress. In this sense, the Nazi superweapons program had long-term impact, though not in the way Germany intended. Yet the broader lesson of the Nazi superweapons program is clear: technology cannot substitute for strategy. Advanced weapons, no matter how innovative, cannot compensate for the loss of industrial capacity, fuel supply, trained personnel, or geopolitical advantage. Germany's investment in superweapons produced some of history's most important technological breakthroughs, but failed utterly as a wartime strategy. The weapons arrived too late, in too few numbers, and in conditions that made their success impossible. In the end, the superweapons of Nazi Germany stand as symbols of the regime's contradictions, extraordinary engineering combined with catastrophic decisions. They reflect a nation capable of scientific brilliance, but trapped in a failing military system. They demonstrate the limits of technology when divorced from realistic planning, sustainable logistics, and strategic discipline. Their legacy belongs not to the Third Reich, but to the world that emerged after its destruction, a world shaped by the lessons, technologies, and cautionary examples left behind by one of history's most ambitious but ultimately futile weapons programs.